So it was 20 minutes each project, no? Yeah. Hello, I'm Martin. I'm the sales manager, R&D of Enjoy Concrete. A little explication. We are architectural concrete company in private housing, but as well in corporate and public. 60 people, less than Cordial. The goal of my presentation today, I wanted to share information, of course, otherwise it will be hard to stand here. And my goal is that we can inform architects and customers in a right way, so we don't make same mistakes, that we can learn something. But okay, all the solutions I can give them, something you have to find out yourself. A review. Our company, Bernard, who's sitting in the back, started a precaster in '92, and in 2010 he sold this contractor, and we started up at Enjoy Concrete. Yeah, then we had go quite fast. We had already our first projects in 2010. I show some picture later. But we didn't have our own mixing plant on that moment. There was a mixing plant on our ground, but it was from a third company. In 2016, we decided to put our own mixing plant, and then we had another extension. And today, this year, we have another extension. So, a few photographs of buildings we made. So, like I said, private housing and precasting is sometimes a hard combination. It's a lot of study work, a lot of different elements. Big cantilevers. The bachelor house, they say. There's a window inside of the pool, so you can see in the bar, in the cave, who's swimming in the pool. We have 8 meters of cantilever here, but we suspend the panels at a steel structure, which was bending 7 centimeters. So if we did that this way, this corner would hang 7 centimeters down. Patterns, sandblasted concrete, acid-etched concrete with white cement, polished furniture, and this is a nice one, rammed concrete, like they mostly do in situ on the place, but we precasted it. It was a panel of 9 meters, all by hand, so filling up with buckets. As well for a part with white concrete. And that's one I wanted to stand still as well, because here we have some message. It's an artwork. We use fabrics to make it. It's 7 meters high. There's a pole in the sand, which is 13 meters because it's sometimes in the flood, like you see. But the artist who made the artwork, she asked us to make it without cement. But at that moment, and still today, and this sea aggressive atmosphere, we said, that's no way, we need cement. But okay, we made a promise that we will follow up and that everyone's working on it to make it better, and that's what I heard this 2 days. So. Good. Now I start with UHPC. We choose to use a premix because of different reasons. They came before, so I'll go fast. We have a perfect water content, no variation because as well like humidity and sand, which is always change. For these UHPC mixers, they're so fragile, so it has to be on the point. So that's the reason we only go for the premix. We tried it once with BASF to make it ourselves, and even on laboratory scale, it was hard. So you can imagine what will happen in a big production. So, like I said, we had UHPC in 2010 for the first time. We used the product FX. It was made by CCB. Then we had a break. Then we had a second period. We used ductile. So we have a bit experience with but the most important thing since 2019 we were using Extreme, the Aalborg Extreme, and we stick to it. So we like it. I show you some pictures from the first period and why we stopped for a while with it. So we made these tiles here, these black tiles. And they were curling because the shrinkage was not under control. That's the reason we stopped at a certain point. But you could do beautiful things with it. We made our desks on our own company, and they're still there. They're black concrete, but inside, so that's a little bit easier. We made furniture, like here, I took this picture because this is the plate of Alvar Aalto, who was the architect of the building here in Aalborg. But okay, red concrete and less the aggressive. Sometimes you have juice or something like, which is acid, and we see on this UHPC concrete, it's less infected as well. So that's one of the reasons, together with the thickness. That's another one with the pit fires and built inside. I like it. So, like I said, we had a break, and we wanted to check out the market because of this curling, which was not under control. And it was not, at that moment we said, it's not usable for structural applications. So, at a certain moment, we had the chance to work with Ductal, who has the experience in Moussem and Marseille, with bridges as well. So we made things in our showroom. We made a showroom. We put lames inside. We made some balconies, and we warmed up the architects to work with it because they don't know the product. So you have to make a market sometimes. So and that was in 2016. And they started up some projects, and they came with questions: how do you make this balcony suspending on this building on this small thickness? And so we had to find out some this information. Sometimes we need an engineering company, but it was a hard way, and we didn't have a lot of support from Ductal. So that was a little bit a hard one. The product is not bad, but we missed a bit of the support. And we had a good support from Aalborg from in the beginning. So, and on the other hand, the shrinkage was less than the Ductal. So that was our biggest reason that we choose for Aalborg. So I go over the projects. That's what I said before. 4 projects, multi-housing 2 times, hotel, and then the 2 bridges you saw already a picture of. Here we had frame terraces, which is easy to suspend because you have a big cantilever on the facade, but they are hard to make. And the reason they are hard to make, I will come on it a little bit later, but it's because of shrinkage at young age. But that was our first project, so we had to build up experience with engineering companies and a lack of norming in Belgium. So we looked to the French, to the German, to the model code, but all these things together, we have to make the puzzle with an engineer, and okay, it has taken time to, and that's important that go fast enough, because at a certain point you convince an architect to work with UHPC, and then it go too slow because you have to find out and they lose the trust. And so this is an important thing. We need to support them with very fast with information. We need a library of, by example, all kinds of fibers and mixtures that we can go very fast in our calculation software as well, and provide them with the necessary information. What we discovered here for these elements, that was the shrinkage at start bending time. So the shrinkage you showed before, that was after 24 hours, I think. But in the beginning, in the first 24 hours, you have something completely different. There's a big shrinkage. And because we have this internal frame, like you see here, in the formwork, we had problems with cracks in the corners, of course. And that happened after 6 hours, more or less. So we had a battle between curing the element, leaving the formwork as long as necessary to have begin of binding. Curing as well protected from temperature, but on the other hand, we had to take it, the internal formwork, fast enough out the element, otherwise we had cracks. So on the graphics on the right side, you could see what happened with the temperature and on the element. In here, it stays in the mold, and here it's if you demold after 16 hours. At a certain moment, you get the temperature on the surface and the internal temperature. This is the surface temperature. This is internal temperature. It's going up, and then it's going fast down. And like here, the difference in between, sometimes when the concrete is not strong enough, the difference in between is dangerous because you have risk of bending. So we had to find out this, and in fact, after 6-7 hours, we did put our internal formwork a little bit loose, but still supporting. It's called shrink 1 centimeter, more or less. Then the second thing we discovered is the relation between the rebars and the air holes. Because it's architectural concrete, they don't want to see air holes, but it has extremely a lot of small rebars, like you can see here. This was a stainless steel rebar reinforcement in the corner. And if we make samples, we didn't put rebars inside to, by example, see the color. And there were no air holes. And then when we started up with the project, we saw air holes coming. And then we saw the relation in between. Here I show you the mortar cone test. And first is the flowing of the concrete. And the reason we take air when all this concrete is passing. It's always fuel from the side, which the more air put into it. The second one is the mortar test with the fibers inside. These were as well poly PVA fibers inside here. And we still had 29.5 centimeters on the mortar test. Another thing we discovered is the fragile elements, that you have to be care of all other things. Normally, these elements in concrete, they are that robust, so you can handle them. But like here, we put them, after we demolded, we put them on polystyrene. But because of this working of the polystyrene, like, what do you call it? Weer in the bedding. No. It pressed up in the middle, and we had some cracks in the corner again. So all these things, all these extra things you have to find out. But, okay, all these things we find out quite quick. So I think we planned in time, and we had a nice result, as you can see. Second job here is more different elements. We had balconies, we had like this L element on top, and we had the lames. Okay, the visible measurement here was 8 centimeters. But in fact, we had even something reservation for the water, so it was only 6 in here. So I think it's quite easy to see that it's necessary to use ultra high pressure concrete for that. We made it up. We split the structure from this balconies. and it's a suspended plate, like you can see here. And this was a structural concrete balcony. Because we have a small and a big balcony, and we were afraid that because of the bending, there will be a difference in the height of the elements. And because they're so small, this small difference, by example, 1 centimeter, will be very annoying. The bigger the elements are, the less you can see it. The results, good. The architect was very pleased with it, and we have to put another building in the same street and the same materials. Third project, we made all these lames. There was 1 kilometer of lames, which are sun lames, but as well they used for the green of the plants growing. And here, because it's very simple here, we have one element, and what we did to make it easy for all the calculations, we made an element, we provided it with different kinds of fibers, and we tested it. So we just bend it, and we had 3 tips of all these elements, and we could save on this is the maximum height of the element, and we have to separate it because, by example, here these elements, they were 5 meters, I think, and there was the question, what is possible? How thick can you make it? But we did it that way. Yeah, you have to find out solutions yourself for the suspending or the connections with the building, because the standard solutions by Leviat, Halfen, Fixinox, they're not always made to place them in these small elements. And that was one we did here, because what was a difficulty, as you can see, these are balconies, so the balconies, they were going this way after they put away the support, and the small elements, they can't support this balcony, so we had to separate them, and we placed all these elements afterwards. And on the top of the element, there's a possibility of deflection. So that was a solution to place the elements after, not in the building phase, but afterwards. This is the result. The green still has to come, but I think it will be okay. And then we had 2 pedestrian bridges with had a span of 16 meters. And the beam here was 7 centimeters thick on 25. So we had to use metal fibers, galvanized metal fibers we used. Okay, you had to calculate with the FR1, FR3 values. I don't know if it's interesting to go very deep in it. But what we saw was that's important. That it is important that you have all these values ready. That you have a library, like I said before, with. Because if you have to test every mixture again and again, it takes too much time, so you have to go faster. And Bekaert had, together with Aalborg, already a test programma with this 80 kilo of 3T fibers on the extreme. So these were all known values, so we could go fast and calculate fast. Okay. To have an idea of the thickness and the height, you can see here how fragile, small, fine the element is. And this was the result. And the reason they choose for ultra-high pressure concrete was reasons of maintenance. Normally they work with steel, but they don't have to paint again. It stays forever or for a long time.